Think Forward. Think Research Channel.
Good morning. I'm Carol Parsonen. I'm Senior Vice President of the Center for Innovation in Science Learning at the Franklin Institute. And I want to welcome all of you today on behalf of the Institute. With us in the audience, but not able to stay, are Dennis Wint, who is President and CEO of the Institute, and my colleague Philip Bohammer, who is Vice President for the Franklin Center at the Institute. I want to welcome all of you to the symposium entitled From the Case Files, an Exploration of the History of Science and Technology, which is a collaboration of the Franklin Institute Center for Innovation and the Franklin Center in collaboration with the University of Pennsylvania Department of the History and Sociology of Science, which is chaired by Ruth Cowan, and she is our host this morning. Dr. Nathan Enzeminger, also of the Department of History and Sociology of Science, and Dr. Susan Yoon of the Graduate School of Education have served as advisors to the Case Files project, and I want to thank all three for their guidance and support. I also want to recognize the Penn Video Network, which is filming this event for the presentation by Research Channel, a global nonprofit organization which is available to more than 22 million households. This symposium is made possible by the generosity of the Barra Foundation with matching support from Unisys Corporation. I want to extend thanks to both these sponsors for their steadfast support of the Case Files project. From the Case Files is a part of the Franklin Awards Week Convocation, an annual event during which the Institute makes awards to internationally renowned men and women of science and technology. The awards began in 1824 when the Institute was founded, and the decisions about who will receive the awards have been made throughout our history by the Committee on Science and the Arts, an independent group of science and technology professionals. The Case Files are the written records of the deliberations of the Committee on Science and the Arts about each potential candidate for an award. There are now well in excess of 3,000 case files which chronicle the greatest names in the history of science and technology over a 183-year period. With a 50-year restriction, the case files from 1957 onward are available to be made public. Seldom in the study of history does one have access to a very significant body of unique and unknown primary documents. The case files offered just such an opportunity in the history of science and technology. In the case files are the recommendations of the committee on particular individuals, published works by candidates, correspondence between members of the committee, between committee members and candidates, pictorial representations of inventions, and a host of other documentary records. Altogether, these documents are a singular treasure for scholars, pre-collegiate teachers and students, and avocational students of the history of science worldwide. The Case Files project builds on the Center for Innovation's early work in using digitization to make the historical collections of the Franklin Institute available to the online public. In 1998 and again in 2003, Karen Ilinich, who also directs the Educational Technologies Program Department, and John Elvidi, our senior curator, developed online resources based on the Wright Brothers Aeronautical Engineering Collection to celebrate the 95th anniversary and centennial of powered flight. The Case Files project has selected case files under 5 themes for digital presentation. The themes last year were energy and communication, in keeping with the tercentenary of Benjamin Franklin's birth. This year, in concert with the Franklin Awards focus on human-centered computing, we have presented case files that represent pioneering work in the development of computing, with particular attention to the seminal work done here at the University of Pennsylvania, together with case files on the themes of transportation and the nature of the cosmos. You will hear from 3 speakers today who will offer their perspectives on the Case Files project, especially the experience of developing the digital resources and the value of the materials that are presented for teachers and students across the K-20 continuum. Dr. Nathan Enzeminger will speak first with a focus on the case file presentations on the history of computing. He will be followed by Natasha Federer, a Penn graduate who has worked with the Institute as a consultant throughout the project in developing the materials for online presentation. Karen Ilinich, director of the Case Files project, will then present a tour of the website and speak about its potential uses in the K-12 classroom. We hope to conclude with some time for question and answer. Thank you very much for joining us this morning. Now, Dr. Enzeminger, please get us started.
Let me begin by saying that this is an exciting project for me to be involved with. To begin with, as an historian of technology, I would argue that the electronic computer is one of the defining technologies of our age. Computers are everywhere. They're in our workplaces, they're in our homes, we use them for recreation, we use them for school, we use them to communicate. But if we think more broadly about the computer as not just being the things on our desk or on this podium, and think about, say, the microprocessor, which is the computer embedded in other things, then the computer becomes even more ubiquitous. Our car has a computer. It has several computers. Our refrigerator has a computer. Our cell phone has a computer. Computers are everywhere. So that's one important justification for this project, and I'm grateful for the Franklin Institute having done this. But perhaps more importantly, this is a big story. And it's a story that we don't actually know a lot about. Computers are everywhere, but I'm not sure we quite understand what that means and where that comes from. There are aspects of this story that have been really well told, of course, right? We all know about Bill Gates, we all know about Steve Jobs, we know about the IBM Corporation. But as I hope you'll see today, that's just a small part of this larger story. And I think that these case studies have been selected to reveal aspects of this story that aren't yet well understood and really contribute not just to our understanding of this, but the scholarly work that's going on that develops this history. I thought that I would begin with an aspect of this story that seems very simple, and it's a basic question that I explore in my essay introducing the online exhibit, and that is, who invented the first computer, right? This is a question we're used to asking about new technologies. It's the most common question I get asked as an historian of technology and computing. It's not easy to answer. And the reason it's not easy to answer is that the computer has been with us for a long time. The word, or the origins of the word computer, date back to at least the 3rd century. But well into the 20th century, the word computer had a very specific meaning. On the screen, I have one definition of the word computer from the Oxford English Dictionary from about 1938. And a computer is one who computes. A calculator or a reckoner. It's a vague definition, but in the 1930s, most people would have had an understanding of what a computer was, and a computer would have looked something like this. These are computers. They're human computers, but that's generally what the word referred to. It's actually a system of computing. We've got women, in this case, working on machines called comptometers, and together, along with some computational processes, they formed a system of computing. There's a direct connection between these human computers and what we know as an electronic computer. Just to give you a sense of the widespread use of this is another human computer using another computing technology. This is called a differential analyzer. It's an analog technology, but it's a computer nonetheless. This is a computer at the Aeronautics Center using yet another form of computer. You'll notice something similar as I move through these slides. The computers, the human computers, look surprisingly similar. You'll notice they're all women. As we move into the electronic computer period, you'll notice the similarity, right? These are the first computer programmers. They're women. They're working here at the University of Pennsylvania, and they are coming from human computation projects at the nearby Bardeen Ballistics Lab. There is a sense in which the ENIAC, one of the first great electronic computers, is an electronic version of these human computers, very deliberately so. And that's an important part of our story. And the human computing aspect of this ties the electronic computer, or the story of the electronic computer, with some of the great events of the 19th and 20th century, right? We all know we're living in an information age. It's not always clear what that means, but we know that it means communications technologies, transportation, and computing. And that story begins in the 19th century. You get the emergence of new kinds of governments, new kinds of militaries, new kinds of markets, national and international markets that create a demand for new information technologies. And if we had time, we'd talk about all these wonderful 19th century technologies, some of which are computational in the sense that they involve numbers. This is a comptometer from the 1880s. Some of them are kind of crazy. They're the kind of patent medicine kind of technologies that do everything from copying to notation to audio recording. Some of them are remarkably familiar and important to the story because the companies that develop them become crucial early players in the electronic computing market. So this is a Remington typewriter. Remington merges with a company called RAND that made filing systems. They eventually merge with Sperry and a few others, but also the Eckert Mauchly Computer Corporation. And they manufactured the first computer. The Burroughs Company manufactured a set of information technologies that look actually quite remarkably like a kind of modern computer and did computing-related work. They weren't focused so much on numbers as they were numbers and text and kind of data processing in the more modern sense. Burroughs also goes on to become an important player in the early electronic computer industry. I'm going to focus today, or the exhibits focus, and I think rightly so, on this guy, Herman Hollerith. He is one of those people you've probably never heard of, and yet is extraordinarily important for several reasons. And I think he exemplifies, which was what I like about the choice of case files in this exhibit, is that they illustrate larger patterns, and Hollerith certainly illustrates a larger pattern. Hollerith was interested in a problem of data collection and management. Now, he was concerned with the U.S. Census. You know, the U.S. Census is mandated every 10 years. We collect data. It's one of the kind of cornerstones of our democratic system. It's extremely important. It's also hard to do, especially as your population grows and expands. And by the 1880s, Hollerith was addressing a problem that the Census Bureau had, which is they had too much data. The 1880 census had been 21,000 pages long. It had taken 7 years to compile. You didn't have to be a mathematician to realize the 1890 census was going to take more than 10 years to process. And so the Census Bureau solicits new technologies, and Hollerith responds. Now, I'll leave the details to the case studies. Let me just suggest that what Hollerith does is apply contemporary industrial technologies, including certain kinds of card processors, but also electricity, to this problem, and he creates a kind of information factory. And what's important about Hollerith is the type of solution that he develops. He mechanizes data processing in a way that really hadn't happened before. He solves the problem of the Census Bureau in a really astounding and very dramatic way. He goes on to form a company that builds what are called tabulating machines that tabulate, sort, collate data. The company he found becomes a direct precursor to the company we call the International Business Machines Company, IBM, the great giant in the history of computing. So Hollerith is important for several reasons. I just show you visually this connection. This is a Hollerith tabulator from about 1890. This is a slightly more refined version. They've begun to incorporate some of the three main functions of the machine into a single, or in this case, two cabinets. This is a further refined version that incorporates more electronics. It's smaller. It's still a tabulator, directly modeled after Hollerith. This is an IBM tabulating machine. IBM was a globally dominant company 30 years before they ever built an electronic computer. They built tabulating machines. And in fact, IBM's first great computer was the IBM 1401, which was a glorified version of a tabulating machine. And so we see a direct connection between this 19th century history and the 20th. Now, to move very quickly through this story and just highlight some of the other ways in which these case studies tell it, brings us to these two men. This is John Mauchly. I have a not so good picture of Presper Eckert. He's in the lower left corner. Mauchly and Eckert are involved in the war effort, computing ballistics trajectories in the Second World War, and they also imagine ways in which they could industrialize this process or apply new technologies to it. Now, their great innovation is electronics, and what electronics does is it makes things faster. There were other computers in the early 1940s when Mauchly and Eckert are building them. The Harvard Mark I, for example, which was built 3 years before the ENIAC. But they were electromechanical. They were slow. What Eckert and Mauchly do is build an electronic computer. And they can only do this in the context of the war. It's enormously expensive, very difficult, and it's huge. This is the ENIAC, part of the ENIAC, and you can see it occupies an entire room. And one of the distinctive features of the ENIAC is that it's electronic, and what made it electronic are what are called vacuum tubes. These are vacuum tubes. And vacuum tubes are about the size of a light bulb. They generate about the same amount of heat as a light bulb, and they draw a lot of power. And the ENIAC had almost 19,000 of them. And as you can imagine, they broke frequently. And designing a machine that could work with these unreliable components required a lot of time and money, and the ENIAC really made that possible. The ENIAC is perhaps not the first computer by modern definitions of the computer, but it was a public demonstration of what computers can do. And the ENIAC itself leads directly to the commercialization of the computer. Eckert and Mauchly go on to form a company that builds the first computer. They're bought by Remington Rand, and they produce, in the early 1950s, the Remington Rand Sperry UNIVAC. The 1950s opens up computing, but computing in the 50s and early 60s looks a lot like the older ENIAC. They're big machines. They're locked away in special rooms because they need air conditioning and power. They're doing jobs that are numbers-oriented. To transform the computer into something more usable that could be used by more people and for more purposes, we had to make the computer smaller and more reliable, which brings us to the third major case study in this section, which is a study of John Bardeen and Walter Brittain. They won in 1956 the Nobel Prize with William Shockley for the invention of the point contact transistor. It's not a remarkable looking technology as it existed at Bell Labs when they invented it. The transistor was the application of semiconductor technology science to the problem of amplification, which if you're Bell telephones is a problem you need to deal with on a regular basis. It also serves this secondary function as a solid-state vacuum tube. It uses less power, it's easy to manufacture in large quantities, and it's more reliable. And of course, it's smaller. The story of the transistor has been widely told. It's largely been told around the character of William Shockley, however, who's this remarkable, crazy interesting kind of guy. He goes on to form an important company in what becomes Silicon Valley. But it's actually Bardeen and Brittain who do the real legwork, particularly on the point contact transistor. And so this case study really opens up a history that everyone thinks they know, but in fact really don't know as well as they imagine. This, of course, leads to the microelectronics revolution as things get smaller and smaller to the point at which it's feasible to have a computer on your desk or in your car or in your cell phone. And suddenly, when you have small and inexpensive computers, you can do different things with them. You wouldn't build a new room in your house to, say, play digital music. But if you could buy something small and cheap to do that, you would create new ways, not just to experience music, but to create music and share music. And so this story of the transistor ties us into today's personal computer and the internet. Finally, we've got this guy, Claude Shannon, shown here with his electronic mouse Theseus, who was smart enough to solve a maze. Shannon is revealing because he contributes in fundamental ways to the history of computing, but also to the history of most of the modern sciences. But he doesn't build much of anything. Theseus is kind of an exception. Shannon writes papers, but he defines ways of thinking about almost every system as a kind of computational or communications systems. And this has revolutionized modern biology. It leads to molecular biology, thinking of humans as DNA information processors, ecology, economics, anthropology. His ideas are remarkably influential, and yet you've probably not heard much about Claude Shannon. And so when we take all of these together, these case studies together, I think we get an image of the history of computing it's a little non-traditional. It's very exciting because it opens up lots of new questions rather than closing them off by attempting to answer the question of who invented the first computer. Just to bring you back around, I'll let you read my essay if you really want to know the answer to that question. But the answer to that question is no one invented the computer. The computer is many inventions, ideas, processes, people that come together. And what's important about understanding the computer is actually understanding the connections between the science and the technology and the business aspects, rather than trying to focus on single technologies. And again, I think that's what's so clever about this particular exhibit. And it ties together the history of the computer in a way that I think no one else has done. So thank you.
Okay, good morning. My name is Natasha Fetter, and I am excited to be a researcher and writer for the Case Files project. I graduated from Penn in 2005, and I work full-time for Penn Development and Alumni Relations, and I work with the Case Files on a part-time basis, and I've been working with the Education Technology team since August of 2004. The process of completing a case file is relatively straightforward. I am assigned to tell the story of an individual scientist and his or her work, and I begin each case file by looking through the digitized images of primary documents which have been pulled from the Franklin Institute archives. These documents usually include correspondence sent between the Franklin Institute and the scientist being recognized with an award, press clippings, and photographs. And you can see some examples of that on the slide behind me. And every file contains a report compiled by the Committee on Science and the Arts, which is the committee responsible for selecting award winners. Case files also contain messages sent among committee members and supporting documents used in the award recipient selection process. Generally speaking, I start with the Committee on Science and the Arts report because this report indicates to whom the award is being presented and why, and it also outlines the scientific function and implications of the invention or theory that is being recognized. I then begin learning about the scientists themselves and also about the science behind each case file using various sources. I use books, which I usually get from Penn's Van Pelt Library. I use reliable online education sites like the wonderful Wikipedia.com, And I also use online biographies of scientists, which are connected to accredited universities and research institutions. I reach out to university archives departments to search for and secure images of the scientists I research. And I do that because I particularly like to include photographs that show the personality of a scientist and also photographs that orient the viewer in the time period in which a given scientist is working. The photograph here is one of my favorites. It shows the spirited personality of Shannon, who is one of our pioneers in computing and communication. And the photograph here shows us the interior of Albert Einstein's office in the Institute for Advanced Studies at the Princeton University. So please note the chalkboard, which shows us that Einstein realized that E equals mc squared, among other things, in the years long before computers, smartboards, and dry erase boards became commonplace in classrooms. So I don't know if that makes you feel better or worse, but it's an interesting point to consider. I myself am not a scientist. I would describe myself as more of a science and history enthusiast. My bachelor's degree and my background is in English, and I actually feel that my limited background in science helps me to discuss the case files in a way that the general public can really understand. The point of the Case Files project is not, fortunately for me, to teach the public about science in an academically in-depth way. Rather, the Case File project aims to show the public that science and the process of science research and scientific discovery is an interesting and intriguing one that is really charged with human energy and human emotion. With the Case Files project, we hope to create a framework for understanding of science as something that's interesting and alive, and scientists as people with whom the public can really connect. To this end, when I research, I make an effort to zero in on biographical tidbits of information about the scientists, which I feel would be interesting to the public. And I also try to include quotes and anecdotes which reveal something about a given scientist's personality or experience working with science. This is one of my favorite quotes, and it's from our friend Albert Einstein, who, as he was nearing the end of his life, said very humbly, "For the most part, I do the thing which my own nature drives me to do. It is embarrassing to earn so much respect and love for it." And one of my favorite anecdotes involves Presper Eckert and John Mauchly, who are co-inventors of the electric numerical integrator and computer, better known as the ENIAC. An ENIAC was a wartime project, as some of you may know, and it was developed with the purpose of improving firing tables. And firing tables are data tables that were necessary for aiming weapons properly and accurately during World War II. So this was a pretty important undertaking for our military might during that war. And in order to get government funding for the ENIAC, Eckert and Mauchly had to present their idea before a board of military officials. And the story goes that on the way to this presentation, Eckert and Mauchly were frantically rewriting their proposal, redrawing the designs that they were going to present, while the military contacts who were driving them to the presentation were wondering how these men were ever going to pull off a presentation that was going to be successful enough to receive military approval. Needless to say, the proposal was in fact approved, and the ENIAC project received funding and went on to receive much fame and recognition as well. So what my research has shown me is that it's really not difficult to make science and scientists interesting. In fact, I have the most trouble when I'm trying to pare down all the information I acquire into the text, which ultimately ends up being published by the education technology team. And the opportunity that I've had to work with these files has helped me to identify some distinct features of the progress of science research. And there are several points which I see as being particularly well illustrated by the case files. First, if you review the files chronologically, you see the process of science research going from a sort of informal, anything goes one to science research becoming a formal, funded endeavor, which is largely tied to research institutions and research universities. So this is a photograph of William Burroughs, who invented the first adding machine in the 1800s, along with a photo of his invention, which was called the registering accountant. Burroughs completed a large portion of his work on a few feet of bench space, which he rented from a brick workshop. Years later, as I mentioned in the ENIAC anecdote, the proposal for the first computer, or well, maybe arguably not the first computer, received funding and was built right over there in the engineering school on Penn's campus. We see most of our scientists of the 20th century and later connected to research universities and laboratories. Albert Einstein worked at the Princeton University. John Bardeen and Walter Brittain developed the transistor in Bell Research Laboratories, and Claude Shannon was a faculty member at MIT, as well as a pioneering force in communication theory. Usually, these scientists are supported by research grants, and they're given access to state-of-the-art research facilities. So they've come a long way from Burroughs' workbench in the brick factory. A second thing you will notice as you progress through the files is an increase in publishing and sharing of science research. In Claude Shannon's case file, we have a nice quote from the Committee on Science and the Arts report that tells us that Shannon was able to synthesize and build on existing research when generating his mathematical theory of communication. And our quote tells us, Dr. Shannon has recognized that complete communication processes can be studied by statistical methods. In many cases, there is considerable background in the literature regarding the properties of the models he has selected. He has organized this material into a comprehensive theory. And by all accounts, Shannon himself made an effort to credit his colleagues for their contributions to communication theory. Moving back a few years to the Bardeen and Brittain case file, we see a different twist on the concept of publishing. With this case file, we have a controversy over who is actually responsible for developing the transistor, which was an invention critical to the success of communication and computing technology. Shortly after Bardeen and Brittain published the version of the transistor they developed, their colleague William Mauchly published his version of the transistor, which some accounts tell us that he developed secretly and somewhat shadily in his basement while other people were working on the transistor in the public space of the Bell Research Labs. And several accounts also indicate to us that Mauchly was not too amused over the fact that he was not the first to publish his theory. So these case files show us that publishing was, in the case of Bardeen and Brittain, a competitive process, and in the case of Shannon, a collaborative one. So these case files show us kind of both ends of the spectrum with respect to publishing. You will also find that the case files show the development of scientific theory and a deepening interest in the farther-reaching implications of scientific discovery. In the earlier files, we see a lot of inventions developed to serve a very specific purpose. Burroughs' adding machine, which we talked about earlier, was built specifically to improve the accuracy of accounting. Hence, it was called the registering accountant. In the later case files, scientific theories are developed to extend beyond one physical invention and to help pave the way for future developments in science. Einstein used his theories of relativity and quantum physics to make predictions about the nature of our cosmos. And Shannon's mathematical theory of communication showed that all elements of a communication system could be represented using statistics and could therefore be related to one another in a precise way. So that enabled communication and computing technology to become more accurate overall. The advent of scientific theory makes the science component of our case files more complex and more abstract, and in my opinion, much more confusing. But for me, it was nice to see that even the members of the Committee on Science and the Arts sometimes had some trouble grasping the science. And we see this in the words of one of the committee members who was working to compile the report on Shannon's mathematical theory of communication. And he wrote, "The language of statistics and probability is a difficult one for me. Although I spent an aggregate of perhaps 60 hours in preparing material for this report, I did not read completely or with full understanding all of the papers on the subject that were available to me." So there is also a great deal of overlap among our scientists. Their inventions, their theories, and their lives often intersect. This is a photograph of Dr. Oswald Veblen, who is chuckling outside of the Institute for Advanced Studies at Princeton University. And Dr. Veblen is going to illustrate this point for all of us. Veblen was a colleague of Einstein's, and he actually played a key role in bringing Einstein to Princeton. And his name appears again in the Eckert and Mauchly case file, where he was largely responsible for the commissioning of the ENIAC. Veblen was one of the officials who listened to the somewhat harried presentation given by Eckert and Mauchly in the 1940s, and who understood the value of their ideas before they could even get through that presentation. Veblen is said to have leaned back in his chair and raised a hand for silence midway through the presentation. And of course, everyone thought he was going to stop them and say, no, no, this is ridiculous. There is no way we are funding this. But instead, he turned to one of his military colleagues and he urged him, just give them the money. So the scientists featured in our case files were extremely bright. They were extremely accomplished, and they were also extremely human. The ENIAC team pulled all-nighters over there, which probably some of our students did last night getting ready for finals, to make sure that their project was completed in time to be useful for World War II. In a moment of frustration, John Bardeen threw a model of the transistor he was working on into a thermos of water, only to discover that doing so actually made the transistor work better than it had ever worked before. And Claude Shannon, in addition to working with complex mathematics and communication theory, liked to juggle, and he was proud of his ability to do so while simultaneously riding a unicycle. And unfortunately, we don't have a photograph of that, but we do have many accounts that Shannon rode his unicycle up and down the hallways of Bell Research Labs while juggling. So we hope that the stories told by our case files will make science come alive for visitors to our web pages. And now I will give you over to Karen Alinich, who will talk specifically about how the case files can enrich K-12 science education.
Good morning. I'd like to spend a few moments to think about the role of the history of science and technology in K-12 science education. So, where shall we begin? It seems appropriate to begin where science teachers have to begin, with the National Science Education Standards. A decade ago, teachers were called to follow standards in their classroom practice. And for the most part, in the decade that followed, teachers have developed a strong fluency with an understanding of the content standards. One area of the standards that is perhaps less often considered is the area related to understanding how the history of science reflects an ongoing changing enterprise. I think that what we've already seen here this morning, and what we'll see a little more of now, suggests that the case files are an excellent way to consider how that enterprise of science changes over time. In particular, the case files, as they've been presented so far, document chapters in the history of science and technology. I'd like to focus this morning on the early history of computing, as have the other panelists, as it represents one chapter of the history in science and technology. But what role can the case files play in standards-based K-12 science education? I'm going to premise my comments this morning on the work of two well-known educational researchers and the ideas that they put forth in their calls for science education reform. Over the past 2 decades, there have been strong movements nationally for change in K-12 science education practice. Bruno Latour, in particular, is a name that stands out in the field, and his call is for students to understand at the pre-collegiate level that scientists are social beings, that scientists operate as members of social networks, and that their teachers are fundamentally key actors in that social network. Whether they realize it or not, they do act as members of the social network of science. Another theorist whose work I think applies perfectly here is Richard Dushel, and his theories suggest that science is actually a process of replacing old ideas with new ideas, and that an understanding of how science works is actually very much similar to the same way that people fundamentally learn anything. As we encounter new ideas, we make sense of them and make decisions about how we should replace our existing knowledge. The process of learning and the growth of knowledge in the field of science involve mechanisms in which these new ideas then go on to replace old ideas, and subsequently others build on that. I think that's a theme we've seen reflected here this morning as we look at the growth from Hollerith to ENIAC. We can see how the work of Eckert and Mauchly builds on the work of those who've gone before them. So what that leaves us with some key ideas to think about as we look at the case files. If science education is going to consider a consideration of the history and nature of science, we need to think about things like social networks, conceptual change model. Certainly, Duschel is not the only theorist who's worked with the conceptual change model in education, but certainly he's a key player. The importance of theories. An understanding of how theories are developed and how they grow and how they change is important for science learning. Communication and collaboration gets back to Latour's ideas of social networks and how a scientist rarely works alone. The exceptional scientist works alone. By far, it's a process of communication and collaboration. And also a little bit of creativity in the mix, which is sort of the X factor, which is a little harder to define. So let's take a look at the case file for Eckert and Mauchly in its presentation online and look at some of the ideas we see documented in that case file and how they intersect with theory. As we think about Eckert and Mauchly's work, as we've heard, they worked with research laboratories here at the University of Pennsylvania. They built on work happening at Bell Research Labs. And it was a convergence. The idea of how many different ideas come together to form new theories in science is well documented in the Eckert and Mauchly case. The idea that Mauchly in particular was known for his tendency to develop ideas through conversation. He was very much a conversational thinker. And that's a very common idea as we look at how scientists do their work, the exchange of ideas through conferences, through symposium. We also see that Dr. Oswald Veblen, as Natasha mentioned earlier, was a key player who participated in the network of science at the time, at the network of technology at the time, where we have a way to connect Eckert and Mauchly over to Dr. Einstein at Princeton. In the Einstein case file, which exists within our History of the Nature of the Cosmos case file chapter, we see Oswald Veblen appearing there as a link. If we think about how social networks and social network research exists, we know that there are strong connectors who exist within the networks. Veblen clearly is one of them. And on top of that, Veblen had a connection with the Franklin Institute. So here we have all of these different entities working in convergence with one another to produce new ideas and build the technology forward. Back to Eckert and Mauchly, we see also connections to industry. As mentioned earlier, Bell Research Laboratories was involved in the development of these ideas at the same time, and Eckert and Mauchly paid attention to that. Duschel talks a lot about the importance of theories for learning science, for developing our understanding of what it means to be a scientist. We know that in science there are kind of three levels of theory. There are core theories that exist within a discipline, and then there are soft theories, which are the theories that are sort of in transit. They're new ideas that are being tested and explored. And then there's an outer rim, which are called the fringe theories. And fringe theories are sometimes so fringe that they go away. But sometimes fringe theories succeed in making their way to the core. And perhaps the idea of an electronic computer at the time might have been considered a fringe theory. It certainly would be one that would be worth considering that way. And when you think about how the other intellectuals at the Moore School of Engineering at the time considered Eckert and Mauchly to be absurd. That idea that their thinking of an electronic computer was an absurd idea is an idea that suggests it might be a fringe theory. How then were they able to get from the fringe into the soft theory range and eventually become a core idea? Perhaps it's because they built on others' work. They built on what had gone before. It's this idea of taking old ideas and replacing them with new ones. The differential analyzer, for example, already existed and was a technology that could be built upon. Likewise, Hollerith's tabulating device and the punch card technologies were well-established theories. These were ideas that were proven to work, and therefore, by building on that, by being inspired by those existing technologies, we're able to see how the absurd idea becomes a little less so. It's also true that Mauchly was inspired by his own passion and interest in weather forecasting, pretty much an avocation of his, but one that really drove his thinking about the electronic computer because he just wanted to be able to get more accurate weather forecasts. That took him to Iowa State University to see the work of Atanasoff, who at the time was already devising an electronic calculating machine. That give and take, that convergence of thinking, that exchange of ideas is documented clearly in the Eckert and Mauchly file. So much so that it even becomes difficult, as we've heard this morning, to say just who did invent the first electronic computer. How, with so many ideas converging in ENIAC, it's really not fair to say which person is directly responsible. And that's true in many disciplines in science. It's why many of the Franklin Institute awards are shared awards. It's because the nature of science is very much a human pursuit in which many different people work together and share thinking to advance an idea, a theory, from the fringe to the core of science. Again, also the fact that you don't have to be at the center of study to succeed. Eckert and Mauchly and most of the ENIAC team existed outside of the mainstream of computing research. In some cases, they weren't even fully aware of things that were happening at other institutions because they weren't core members. And that's why they depended so much on people like Veblen, because they were the connectors in the social network. The other activity that was key was the communication and collaboration, the publication of ideas, the sharing of research is how ideas are built upon. In 1946, February 14th actually, the New York Times published an article about the ENIAC, and it was a glowing review because the reporter had been on hand to watch the the press demonstration that took place that day. What we see in our case files on the same day as the clipping is a memo internally that suggests the importance of having the Committee on Science and the Arts look at that new subject, because its achievement, as further tests may prove its dependability and freedom from human error in operating it, you can almost sense the excitement that Mr. Rogers had as he jotted off that quick note internally. They knew there was something, both the New York Times and the Institute's committee members knew there was something special about ENIAC. And that excitement and enthusiasm is discovered as you go through the case file, and that's an important lesson for all students in K-12 science classrooms. Publication continues, of course, and an interesting article that was published in the 1948 issue of Electrical Engineering, co-authored by Brainerd and Sharpless, not Eckert and Mauchly, Brainerd and Sharpless, two of the other members of the ENIAC team. A key idea here is that many people have right to the ideas that exist in the collaborative process of science. And it also starts to get a little messy. It's not necessarily a clean, clear-cut process. Eckert and Mauchly go on to work with a mathematician named von Neumann and develop plans for the EDVAC, a later version of an electronic computer. And von Neumann drafted a report and circulated it, and it became controversial because of his lack of accreditation to all the other people involved. So it's a great little case study about how theories can bump up against each other and how science isn't necessarily always a straight line. This is that last X factor. That idea of a little bit of creativity is probably involved in as well. In order to determine the optimal type of wire to use in that massive computer that filled an entire room, Eckert, in his quest and determination to make sure every decision he made was perfect, he starved some mice, caged them for a few days, and then tempted their appetites with different types of wire. The one they enjoyed eating the least was the one selected for use in the ENIAC. That's the X factor. It's a little bit of creativity, a little bit of creative genius, a little bit of craziness that comes into the equation. Okay, let's just take a quick look at some of the artifacts that are accessible through the online case presentation. In our chapter on the early history of computing, we find the Hollerith presentation, the Burroughs presentation, Eckert and Mauchly, Bardeen and Brittain, and Claude Shannon. Let's just take a moment to look at some of the other things you can find in the Eckert and Mauchly case presentation. Lots of photographs, and lots of documents, letters, correspondence, memoranda, internal reports, the true documentation of the process, and also some ephemera, some items that are presented more for their beauty, really, than anything. Although you can also read the entire story of the ENIAC here through this page-turning device that enables us to turn the pages of the document online. You can also see individual scans of each page. So we're able to magnify the pages of the document and get a close-up view. We can also, of course, take in each page individually and look at it in depth for reading the whole story of the ENIAC project. I'd like to conclude by returning to a thought from Eckert and Mauchly themselves. This is page 2 of the article that appeared in the New York Times on February 14th, 1946. And in that article, Eckert himself predicts that the old era is going. The new one of electronic speed is on the way, when we can begin all over again to tackle scientific problems with new understanding. I think these words certainly inspire all of us as we think about going forward with the Case Files project, as well as with science education in general. Thank you very much.